For decades, convolutional neural networks or CNNs were the undisputed kings of computer vision, powering everything from facial recognition to medical imaging. However, vision transformers have quietly stolen their crown, not by looking closer, but by stepping back to see the whole picture. Welcome to AI Club Pro, where we make AI concepts feel like everyday ideas. Vision transformers are inspired by the powerful transformer architecture that revolutionized the language processing models like ChatGPT. The big idea behind transformers was originally to help computers understand sequences of words by looking at every word in the context of other words simultaneously. But images aren't sequences like text. They're huge matrices of pixels. So, how does the same approach apply to images? This concept was first introduced by researchers at Google in a landmark paper titled An Image is Worth 16 times 16 Words in 2020. They proposed a clever idea: split images into smaller pieces and treat each piece like a word in a sentence. Because images are two-dimensional, these small pieces are patches, and these patches are arranged sequentially before being fed to the transformer. In contrast, traditional image processing methods like convolutional neural networks examine images piece by piece using sliding windows. Much like a small flashlight that is going over the image to identify patterns. These approaches excel at identifying local features such as edges or textures, but then they often struggle to grasp how different parts of the image relate globally. The key innovation in vision transformers is that by treating image patches as a sequence, they can leverage the powerful mechanism of self-attention. Self-attention enables each image patch to directly communicate with every other patch simultaneously, effectively allowing the model to see the entire image in context at once, rather than focusing on local areas. Imagine solving a puzzle where you can instantly see how every piece connects with all others. This global awareness can lead to richer interpretations and deeper understanding, especially for complex tasks like medical imaging or object recognition. Additionally, vision transformers come with built-in interpretability. They can visually show you which parts of the image were most important in reaching the conclusions, making them not only powerful but also transparent and trustworthy. Here's the famous diagram from the paper Attention is All You Need. If you're seeing this for the first time, we have a separate video called Attention is All You Need, Transformers Explained Simply. I highly recommend checking that out first. The original transformer uses an encoder-decoder architecture, which is mainly designed for tasks like language translation. But for computer vision tasks like classifying or segmenting images, we typically only need the encoder part. So how exactly does that encoder handle images? Let's break it down step by step. First, a vision transformer splits an image into smaller pieces, like slicing a photo into equal-sized squares or patches. Think of cutting up a photograph into a grid. Each patch is treated like a word in a sentence. Then the model turns each image patch into a vector, a numerical representation that encodes information about that patch. Kind of like translating visual data into a mathematical language that computers can understand. Once these patches are turned into vectors, the model doesn't automatically know which patch came from which part of the original image. To solve this, vision transformers add a special information called positional embeddings, little numerical tags that tell the model exactly where each patch was located originally. Just like, labels that say this is the top left patch, or this is at the center, or this is at the bottom, etc. Now let's dive deeper into the transformer encoder, the real powerhouse behind the vision transformer. Once we have divided an image into these small patches, they start having a sort of conversation with each other. Imagine each patch looking around and asking, what are the other patches here? Do they know something that will help me understand the whole picture? This patch to patch conversation is driven by something called multi head attention, which originally made transformers famous. If you glance at that paper, you'll see it described in detail under the scaled dot product attention equation how this conversation happens. Here's how it works. Each patch embedding first gets transformed three times, producing three different perspectives called queries, keys, and values. Think of the queries as patches saying, here's what I'm looking for, and keys as patches responding, here's what I have got, and values as the actual information being exchanged. When we combine these queries and keys, we measure how closely they match, forming a sort of similarity. Technically, we calculate this by multiplying the queries and the keys together and scaling and applying a softmax function to get the attention weights. These weights indicate how much each patch should pay attention to the others. Finally, each patch collects information by taking a weighted average of the values from every other patch, effectively summarizing what's important from all around. But here's another twist. The entire attention process does not happen just once. With multi-head attention, the model performs several parallel attention computations, each head capturing a different type of relationship. Afterwards, all these parallel results are merged together, giving the model a comprehensive understanding of how the patches relate to each other. Once the patches have shared their insights through multi-layer attention, each embedding takes some time to independently reflect on what it has learned using the multi-layer perceptron. Essentially, a small neural network that's applied separately to each embedding. Think of this step as each patch embedding processing and refining the information individually, making its understanding deeper and clearer. Finally, after all this communication and reflection, the vision transformer gathers everything it has learned into one special embedding known as the class token. You can think of this token as the model's summary patch. It takes careful notes of the entire conversation among all the patches, capturing the most crucial points. And it is this class token that the vision transformer uses to determine exactly what is happening inside the image. Vision transformers are excellent at image classification. They can recognize objects like vehicles, animals, or specific medical conditions from X-rays or MRI scans. They're also great for object detection, where they can pinpoint exactly where different items like pedestrians or street signs appear in the image, which is crucial for things like self-driving cars. Additionally, vision transformers excel in image segmentation, where they precisely outline specific areas within medical scans such as tumors or damaged tissues, significantly aiding diagnostic accuracy. Beyond these tasks, they are increasingly being used for video analysis, facial recognition, and even interpreting satellite imagery for environmental monitoring. One big advantage of vision transformers is that they can easily see relationships across an entire image without being restricted by local patches. This global view often leads to a better understanding and improved accuracy on complex image tasks, especially when the model is trained on very large data sets. However, there's a trade off. Vision transformers typically require more data to learn effectively because they start without built in assumptions about how images typically behave. Unlike CNNs, which naturally understand local patterns like edges or textures. If you have fewer images available, CNNs might be easier and faster to use. But if you have millions of images to learn from, vision transformers can often surpass CNNs by capturing richer global context. Another thing about vision transformers is how good they are with transfer learning. If you're not familiar with transfer learning yet, we have a video that explains this clearly called Transfer Learning Simplified: How AI Borrows Knowledge. You may want to check that out first. Basically, transfer learning lets a model take advantage of the knowledge learned from huge datasets and reuse it on smaller datasets or tasks. Since vision transformers have rich global insights from millions of images, they are very quick at adapting to new related problems, even when there is limited data. For example, a vision transformer that has been trained on a broad set of images like ImageNet can quickly get the hang of identifying rare medical conditions using a small collection of medical images. However, the effectiveness of transfer learning with vision transformers strongly depends on how closely the new task aligns with the data, which is what the model was originally trained on. Generally, if the new images or tasks are similar enough, vision transformers transfer the knowledge quite impressively, often outperforming CNNs due to their richer global context. On the other hand, if your new task is quite different or your dataset is very small, vision transformers might struggle more compared to CNNs, simply because they start without strong built in assumptions about images which CNNs naturally possess. Also, note that vision transformers offer built in interpretability, something especially valuable in fields like medical imaging. You can visualize exactly which part of the image the model paid attention to. Today, there are many variants of vision transformers designed to be even more efficient, such as the swim transformer, which cleverly focuses attention on specific regions, or data efficient transformer, which learns faster from fewer examples using tricks like knowledge distillation. In short, vision transformers have opened an exciting new door in computer vision, giving us powerful tools that can think globally, reason efficiently, and provide insights into the decision making process. All of this while transforming how we teach computers to see. Thanks for joining us on AI Club Pro. Hit that subscribe button for more eye opening AI insights. Stay curious and keep exploring.